So let's come back to the revealing thermoelectric paradox in semiconductors. So today I will share about the results. So the first one is to come up with the theory of thermoelectric magnetic flux. The thermoelectric magnetic flux and the circulating current are connecting by the formula. The magnetic flux equals to the L times the circulating current. We consider a superconducting thermocouple consisting of a superconductor S and a superconductor S prime with a much larger gap, and hence negligible quasi-particle currents. This situation corresponded with our experimentals. However, it is simple to generalize it to an arbitrary superconductor X prime. By the current conservations, the circulating current is independent of the coordinate x along the biomechanical loop, and the superconducting current. The theory of thermoelectric quasi-particle currents was developed by Garpin and Webster and Van Hardingen. However, calculations of the superconducting circulating current, which generates the thermoelectric magnetic flux, was not attempted. Here, we propose with the calculations using minimization of the total energy of the superconducting loop W with respect to the currents, as suggested by Garvin. See the supplementary materials for details. The total energy consists of energy of the magnetic field created by the circulating currents W, and the kinetic energy of superconducting electrons. We find the circulating current is defined by the quasi-particle thermoelectric currents and the kinetic inductance of the weaker superconductor at the hot contact. Next, we can calculate the quasi-particle current at the hot contact, where S is the cross-section area of the superconductor. We use the heat equation that relates the rate at which the quasi-particle accumulates the energy from the heat flow and the rate of quasi-particle of energy transfer to the local phonos in a wire. And the following equation is the phonon temperature and the quasi-particle thermal conductivity and the material electron-phonon interaction parameters. And then we can obtain the formula and using the connection of the coefficients in the superconducting state to their values in the normal state. And assuming that the normal state quasi-particle thermal conductivity obeys the Weismann-Franz law. We arrive at the following formula for the thermoelectric flux, which is a really complicated formula. And let me prove that the following formula is the effective inductance V is the volume of the small gap superconductor and the function describes the drop in the electron-phonon interaction upon the temperature decrease below the critical temperature. The value of the gap at the hard contact is the smallest within the bimetallic loop, making the contact essentially a weak link. The kinetic inductance of such a link is given by the following formula, where I is the critical current. At temperature close to critical, the kinetic inductance diverges as the critical current goes to zero. The values of the circulating currents approach that of the quasi-particle currents. According to the equation 2, the thermal flux originates from the temperature difference between the heteroelectron system and the phonon system. It is a continuous function at its critical temperature and above it. We started the finite supercurrent I. However, no singularities in the thermal flux are expected at the critical temperature. When the Bach supercurrent fades, the value of circulating currents I continuously approach the value of quasi-particle currents. This is the result of current convergence. Simultaneously, kinetic inductance diverge at the critical temperature, and the effective inductance approach the value of geometric inductance L2. The formula gives several conditions to maximum the thermal flux in the superconducting states. Besides an obvious condition of the large thermal power, the formula requires large effective inductance and strong electron-phonon interaction, as well as coupling of the local phonon system to the environment of the bimetallic loop to ensure difference in the electron and phonon temperatures. The formula is valid when one of the thermoconductors enters the normal state. In this case, by the current conversations, the circulating current is equal to the thermoelectric current in the normal wire. In addition, in this case, G of TQ equals to 1 and effective L equals to L2. And now we are going to the experiments part. And the experimental setup is shown as figure 1. The bimetallic loop is placed inside the measuring loop of a quantum magnetic matters. The characteristic magnetic field B equals to is around 10.5 Tesla, was high enough to allow precise control of K numbers. We use an magnetometers based on the HYQUID, similar to standard squid. The magnetic matrix consists of a superconducting loop interrupted by a weak link. The weak link consists of normal conductor connected to the superconductor at C and D. The electrical resistance R between points A and point B is an oscillating function of the total magnetic flux. Threading the interferometer loop, while R0 is independent of magnetic field and R is the amplitude of oscillations. To determine the determine the thermoelectric flux. We measure several resistant oscillations as a function of applied magnetic field. The value B of Nk of the field at the extrema of the resistance corresponding to the following equations. In the absence of the temperature gradient, the measured values of Bk can be found using the following formula. Examples of oscillations as a function of applied magnetic fields are shown in Figure 2. Figure 2a shows the oscillations in the absence of the temperature gradient at different k numbers. The k numbers were manipulated by thermocycling of the biometric loop between the normal state and the superconducting state in the pre-calculated applied magnetic field. When the k number was changed to k plus delta k, the positions of the extrema was shifted by delta b, which was constant for all maximum and equal to delta b equals to the following functions equal to 0.2, which is an agreement with our design value. When the temperature gradient is established, the total flux corresponding to a particular extreme of the resistance is intact, whereas the major positions of the extrema was shifted to the new values, specifying the equations. We can use the different delta B Nk equal to Bnk minus Bnk prime, the phase shift in oscillations, to determine the thermoelectric flux. The coefficients A equals to delta A over A, and B equals to delta M over L2 describe the phase shift due to the due to the sigma effect, and the phase shift C is associated with the thermoelectric flux and is independent of N and K and magnetic field. B0 is a period of oscillations. To create a temperature gradient, we use a heater made of a non-metallic silver wire connected to one of the contacts of the biomedical loop. Figure 2b shows that the oscillation at a fixed K number at different heater currents. The heater produced two effects describing equation 5, the phase shift associated with the thermoelectric flux and the change in period of oscillations due to the sigma effect. The dependencies of delta B and K over B0 versus N and K at fixed heater currents are shown in Figure 2. They are linear in agreement with equation 5. The slope gives values A and B. Equation 5 at a constant heater currents is an equation for plane in 3D place with XYZ coordinates corresponding to N, K, and delta B over B0. The planes plotted using measurement results as shown in Figure 2e. They allow visualizations of the sigma effect contributions, where is about An minus Bk at different K and N values at a glance. The sigma effect is minimal alone satisfy the relations about AN is equal to BK. Hence, keeping ratio K over N constant and changing P equals to the integral of BK over AN, we can move along the line for these particular samples. B over A is equal to 5 over 2 and K over N is 2 over 5. To decrease error in the value of C, we average measurements at different combinations of N and K. The major values of C as a function of P at several values and N and K are shown in figure 3a. As expected, the value of C that is directly related to thermoelectric flux was independent of K and N and depends on the heat currents. Here, we emphasize that to obtain the value of thermal flux, one has to know the absolute values of N and K. Thermocycling adds integral to the K numbers, where K numbers equal to K0 plus M, where M equals to minus and positive 1 and 2, and so on. And the K0 equals to integral of A2 BR minus phi 0 is the number of flux quanta tree because the residual magnetic field BR is in the solenoid. We have measured BR using sensitive Hall probes and found it to be also to the geomagnetic field B. In previous experiments, the number was up to 5 orders of magnetic larger, leading to a much larger sigma effect. Next, we have undertaken an experiment to verify the major thermal flux, showing the signature of the genuine thermal flux with a change of the sign when the temperature gradient is reserved. We have nanofabricated a mirror reflected biomechanical loop with the aluminum part replacing lead and vice versa. The equivalent to a change in the directions of the temperature gradient and circulations of the thermoelectric currents generates thermoelectric flux. The value of C versus P for the two samples are plotted in figure 3a. The sign of C change when the temperature gradient is reserved, as expected to the genuine thermal flux.